So here's one of the problems that you'll see in your 7.1 homework. I actually grabbed this from an Ask My Instructor email. This is number 6 in your 7.1 homework in my math lab. So you're given a 3x3 matrix, and notice that it is symmetric. I know that in this case everything along the diagonal, it all matches, they're all 6s, but you don't need that. So this could be 6, 17, 24, and that would be fine. It's still a symmetric matrix, as long as when you transpose the matrix, you get the exact same matrix that you started with. So like first row here, if we turn that into the first column, 6, -7, -7, you get the same thing. And then second row, if you turn that into the second column, -7, 6, -7, same thing. Okay, so you get the idea with that. Let me take those away. Okay, now we're given some kind of random information. I mean, the idea here, they don't want you to have to go through all of the steps of minus lambda along the main diagonal and then working out that determinant. And then you're going to have a third degree polynomial. You've probably experienced that can require a lot of effort to solve that third degree polynomial equation. So they're trying to spare you some of that effort by giving you a couple of clues. So they're giving us this vector v, 1, 1, 1. And we're also told that, so 13 is an eigenvalue of the vector, or has to verify that, and that v is an eigenvector. We can go with either one of those first. I'll go with the eigenvector because that's kind of the easier one to deal with. So the fact that v is an eigenvector means there's some scalar lambda such that a times b is equal to lambda times b. And in order to find lambda, I mean, all we really need to do is multiply the matrix A. Let's see, these -7s, we've got 6 down the diagonal, we've got -7 everywhere else. Okay. So this matrix times the vector 1, 1, 1. When you multiply a matrix times a vector, you do first entry here, so 1 times the first column. So that'll give you this. Plus second entry here, so 1 times the second column. So you're going to get -7, +6, -7. And then plus 1 times the third column. Oh, thanks for the tip right now. 1 times the third column, so -7, -7, +6. And so when we do the arithmetic there, 6 minus 7, that's -1, minus another 7, that's -8. -7 plus 6, that's -1 minus 7. And then -14 plus 6, that's also -8. So we end up with, now remember, we want to express this as some scalar times the original vector v, which is this 1, 1, 1. And so this one's fairly obvious. We could factor out -8, and then we have the vector 1, 1, 1. So this is our lambda. This is the eigenvalue that corresponds to this eigenvector 1, 1, 1. Okay, so I'm thinking about where I want to collect this information. Let me erase this. And I'll write down the stuff I want to remember up here. So we found one eigenvalue, -8, goes with an eigenvector. I'll call this one v1, 1, 1, 1. Okay, and then I'm sort of going to go by the process that I gave, that I offered you guys in the notes. Notice we are kind of skipping step 1 here. Find the characteristic equation, use that to identify eigenvalues. That's where I said that, yeah, okay, normally if you're just given a symmetric matrix and said, okay, figure out how to diagonalize this matrix, this is what you would have to do. Thankfully, in the homework, they're pretty much always giving you eigenvalues. They're giving you something to start with. So you're not going to, I don't think, ever have to fully do step 1 and step 2 the way I'm describing here. But in general, this is how you would diagonalize a symmetric matrix. Okay, so that's the first one. Let's go with, what else? Oh, 13 is an eigenvalue. Okay, so let's think about that. And I'm going to erase again. Move this out of the way. Okay, so if 13 is an eigenvalue, that means that there's some vector, think about what I want to call it. I'll call it x, because that's what I called it in the write-up. So some non-zero vector x, such that a times x equals, okay, eigenvalue 13, so 13 times x. This is our lambda. Okay, and so we want to solve this equation for the vector x. So I can think back to solving an algebraic equation from your early algebra days. Normally when you're solving for a variable that appears on both sides, normally you would move your x's all to one side and then factor out x. Now I just want to be careful here. This 0 right here is the 0 vector, because a times x is going to be a vector, and then 13 times x is a 3 by 1 vector. So here you got 3 by 1 vector minus the 3 by 1 vector. So this is not just the number 0, but the, like this guy, 0, 0, 0. Okay, so when you factor out x, the vector x, a minus 13, so you can't do just a 3 by 3 matrix minus 13. That operation doesn't make sense. But I talked through this back in chapter 5 about how we can get away with expressing this as a minus 13i, the identity matrix, times x. And like I said, we saw the details of that back in chapter 5. So I'm just going to go ahead and do that. This is the same way we were finding basis for eigenspace back in chapter 5. So this guy, okay, and so that can be expressed as an augmented matrix where you've got a, let me get a different color, and then we're going to subtract lambda from the diagonal entries. Again, just like finding a, I mean, this is essentially what we're doing, is finding a basis for the eigenspace, like you did in your chapter 5 homework. So if you were wondering about the details about why are you just subtracting it from the diagonal, then look at 5.2, I think, is where you're going to see that. Either 5.1 or 5.2. Okay, so when you do that, so you have 6 minus 13, that's negative 7. All of these are 6 minus 13, 6 minus 13. So these diagonal entries that were 6s, you're subtracting 13 from each one, so you're going to, all of those turn into negative 7s. And then actually we had negative 7 everywhere else to begin with. Those entries are unchanged. So when you do your a minus 13i, you get this matrix with a bunch of, with negative 7 everywhere. And then if you did row operations, you would do like negative 1/7 times everything. This would become just a bunch of 1s. And then you would get rid of row 2 and row 3 because those are just repeats of row 1. So you're going to end up with this for the reduced form. And that's something where you wouldn't need to show steps. Okay, and that means that in your entries for x, so if we think of x as this x1, x2, x3, for the entries of x, then x1, when you move these guys over, is equal to negative x2 minus x3. x2 and x3 are your free variables. So x is equal to x1 is negative x2 minus x3. x2 is a free variable, so x2 is just x2, and x3 is just x3, another free variable. And so you can break that down into x2 times the vector negative 1, 1, 0, and then x3 times the vector negative 1, 0, 1. Okay, so a basis for your eigenspace corresponding to eigenvalue 13 would be these two vectors, negative 1, 1, 0, negative 1, 0, 1. These vectors are linearly independent. Neither of those vectors is a multiple of the other. You can tell that by the 1s and 0s in the second and third positions. But if you take the dot product, it's 1 plus 0 plus 0. The dot product is 1. So they're not orthogonal. And in this diagonalization process, we do need orthogonal vectors as our columns of that diagonalizing matrix P. We need the columns to be orthogonal. So these two vectors aren't going to work, unfortunately. What we need to do then is apply Gram-Schmidt process. We have a process for taking a regular basis and turning it into an orthogonal basis. That's exactly what Gram-Schmidt is designed to do. So that's going to be the next thing that needs to get done, is apply the Gram-Schmidt process to those two vectors. I should pause the recording while I erase, but I'm not even that tech savvy. No, I could if I was willing. Anyway, okay, so Gram-Schmidt, I'm just going to do G-S. That's what we're doing right now. We'll use as our first vector, remember with the Gram-Schmidt, if you look at your 6.4 notes, we let V1 just be V1, whatever the first vector is in your set. So -1, 1, 0. We'll just take that vector as it is. Then for your second vector, you do x2 minus, so x2, I know I'm using x2 in like two different senses here, but by x2 I mean the second vector, this guy, minus the projection of that vector, or the component of that vector that's parallel to that first vector. And so if you've had Cal 3, it is the projection of that vector onto V1. We want to get rid of that. The idea is you take this second vector, if this is our V2, and let's say here's V1. We want to decompose V2 into, part of it is just running along V1. We don't need that part. The part that we need is this part that's orthogonal to V1. So, I'm calling V2 two different things. But just that's the general idea. My naming is not good in this video, but hopefully you get the idea. Okay, and so the way we do that is we take the dot product x2 with V1 over V1 dot V1, and that's our multiple of vector 1 that we need to subtract. So let me write the actual vector. So it's the second vector in the set minus the dot product of this vector with V1. V1 is, see, the hardest part of this part of the process is using the right vector in the right place. Okay, so here's x2. Okay, that's the part. This is x2, this is x2. Okay, good. Dot V1. Here we go. Over V1 dot V1. Times V1. So let's see, this dot product would be 1 plus 0 plus 0, so 1, over 1 plus 1 plus 0, so that's 2, times this. Okay, so that gives us, and the timing for this video is about to run out. Let's see if I can finish this part. -1 plus 1/2, 0 plus 0, 1 minus 1/2, so that would be 1/2. Okay, and then I'll pick up with a part 2 for this video.